G'day guys, we're going to look at double D coils and why the older ones, most of them, are pretty pathetic, especially with machines that are clocking higher and utilizing more gain. This is a fundamental fact that we have to deal with these coils. Let's go through the whole thing and I'll show you why it's so woeful that you should be using mono coils, or if you're going to use double Ds, they have to be completely redesigned. They are atrocious the way they work, and I'll explain. First of all, I have a resistance or multimeter, resistance meter. It's very, very accurate. You can do internal compensation and have what it reads is what it reads. I can even run a 4-wire system where I can actually take the extra wires out and it bypasses its own leads. So you can compensate that way as well. But for this, we don't really need to. Here I have an LCR meter, which is L for inductance, C for capacitance, and R for resistance. This will do it at 2 frequencies. It'll test things at 1 kilohertz or 120 hertz. Basically, you do most of your tests on the low end because then you start getting reactance and the resistance goes higher. The faster the frequency is, the more reactance you get, and you don't get a pure ohmic resistance reading. That's what we're looking for here. Not that it works that way. It does work in a reactive state, but we're going to just compare basic DC function, which is a measure of power to get in and out. So yeah, I just got a coffee here, which I'm going to drink because my voice is, yeah, had a night on the terps last night. Yeah, still not fixing it too well, but anyway, we'll persevere on. Now, let's have a look at some fundamental things. Fundamental things here. Here we have a mono cable and a double D cable. Now, if I actually measure these, and this will probably be of interest, the double D cable is actually a little bit shorter than the mono. Maybe it had an issue and it was cut short. I don't know the history, but it is what it is. So performance-wise, the mono cable should perform a little bit worse by about 5%, but it won't. First of all, let's have a look at the double D cable capacitance. This is a critical area of coil design that's overlooked by most people. First of all, let's do it on this. We got short leads on here. It's adding about 3 picofarads of capacitance, which is sweet FA. So I won't worry about that too much. So what we'll do, we will put it into capacitance. I don't know if you can actually see that. Yeah, it's not backlit or anything. This is ancient, but it works really well. So what we'll do, let's look at the capacitance on the transmit pair. This is the spiral braid and the inner. There's 2 sets of cables in here. This is your transmit here, and that's your receive there from the receive coil. So here we go. This is on the transmit on a double D. This cable, right? You're gonna know the history because of what it is probably, but 256 picofarads. Thumbs down. That's woeful. That's woeful. Well, that's what the detector sees. Let's do the receive windings. The receive windings, receive windings. Well, if you have a look at the cable size, I'll just strip it back a little bit. The transmit is larger and the receive is smaller. So there's very, very few strands of wire on the receive. It's a very small gauge. I don't know what it is. I haven't measured it. But the thickness of the bundles, basically, if you have a bundle like this of wire, say it's a big piece of wire, and the outside's like this, what happens is the more closer this is to that, the capacitance goes up and up and up and up and up, and then it touches it and short circuits. No, but if it's out here, it's very little capacitance, and as you make the overall diameter of the wire smaller, the capacitance goes up. So with this big bundle in the transmit, I don't know if you can probably see through that, it's very close to the braid, so it has high capacitance. That is very, very high. That I'll tell you what, on a modern detector, double D cable will have a huge performance impact. Okay, so let's have a look at the actual double D cable. Doesn't matter which way you put it round, it's just a capacitor. So on the smaller wire, have a look at that. If you can see it, I'll just read it out anyway. It's 164 picofarads. Take off 3 picofarads. Say 160. 160 is still woeful, right? It is 160 picofarads. What that does, it tries to slow down the transition of decay signals or anything, any signal you're putting through that's and anything oscillating, anything doing a transition from a energy level to a lower energy level. Instead of going like that, it does this, right? And you lose the signals, okay? Capacitance eats up your tiny signals. Hard to get your deep signals. It's an enemy of efficient detecting. So there you go, 164. I wish I measured this a long time ago, right? Because I never thought it was that high. But anyway, there it is. And it's not even as long as a mono. Let's have a look at a mono cable. Just 2 pair. It's a foamed polyethylene dielectric and spiral braid. And I just chopped that off a coil very close to the windings. So that is a mono cable. Let's have a look. This is important stuff. This is the basics of detecting, right? You got a crap coil, you're going backwards fast. And when we modify detectors and you start clocking the detectors faster and faster, the high capacitance in those woeful cables slow down the transitions and also the decay rates, and what it basically goes pear-shaped. Okay, so that's one of your big limiting factors. Also the coils themselves. I'm going to get onto that in a second too. Okay, stick that on there, stick that there. So it's a big fat mono cable. Look at that, 103 picofarads. Take off the 3, 100 picofarads, and it's longer. This is why, a good reason, the monos are killing the double Ds now with the faster detectors, with the fine gold modes, even enhanced mode. If you get rid of the capacitance, up come your signal levels big time. So why do monos outperform the double D coil? So that is very, very low. I couldn't get over the difference in 100 picofarads against the other one on the transmit lines, 256. My God, that's, if you look at it in capacitance terms, probably 4 times the losses. Anyway, the signal's got to go up and come back. Anyway, that's mono cable. Now, let's have a look at the construction of a double D cable. Coil. Cables, coils, whatever. Okay, as you know, they're all made of foam, hopefully, full of air. You want as much air, tiny little air bubbles in this as possible. You don't want a big, fat, thick slab of plastic or anything like that. There is an issue with dielectrics. Dielectric means the lower the dielectric, the less overall attenuation of your signals surrounding the cables, wires in the foam itself. And that's why it's important to have a foam dielectric in the middle of the cables that surround the center conductor. You don't want horrible insulation material, that's got a high dielectric because it causes losses. Go read up dielectric losses and all that sort of stuff. If you really want to get into it, I'm not going to bore you with it. Okay, so here we go. Here's our transmit coil on here, and you can see it's just the normal 1mm square type litz wire. Okay, whatever the strand, it's probably 72 strands. Odd, it might be different. Don't know. I haven't peeled it back and looked. Not important at this stage. But have a look at the receive winding. Okay, now the receive winding is, first of all, it's potted in resin. That resin has a dielectric of a house brick, right? In other words, it slows down the operation of the coil, especially if it gets in the windings. It greatly increases the capacitance. Between the windings, it slows down transitions and loses signal, okay? The other thing too, this is probably not so much of an issue because we're not putting a load as such, a low impedance load on the end of this coil. But even so, if you have a look at these when it was made, it's probably all around here. No, I've taken it out. But if you have a look at how thin the wire windings are here, if you grab them, they're that thin. It's like thick hair. They're litz wire, but I don't know if you can see. Have a look at that. Right? That is very, very thin. And this is where you get the unbalance in these coils. And they're going to run a little idler type puck of wire. Oh, there it is here. See under the tape? That they do that to null it, to null in this part here. You move it around and get a null. But anyway, why? Right, anyway. The other thing these have on the winding in here, on this, they put usually a 560 ohm resistor across the windings. First of all, that's a constant load on that coil. So there's no switching it out or switching it in. It's there all the time. It is chewing up receive signals, basically trying to, through a resistive load, short it out. Okay, so it's one of these, it goes pear-shaped type things. But the way, the amount of, it's got extra turns on it, by the way, on the receive coil. This may have 20. This one here, I don't know, because I've never counted it, because it's all has resin poured in, and if you try and take it out, it'll snap and break in half. It's brittle as. It's basically filled up with eraldite. That's what it is. But we can measure the wires here, and we'll just see some of the function. This one here is about either 280 to 300 microhenries. They're all around that number. So let's clip it on here, and we'll measure the actual, well, first of all, let's have a look at the resistance. So I'll calibrate this one. I could use the other one, but I've got clip leads on here, which makes it easier. So yeah, it's saying 0.042, but all I do is hit the calibrate with the thing shorted, and come on, it should just calibrate, shouldn't it? There we go, 0.000 ohms. Okay, so it's very low. So now, because it's calibrated, we don't have the resistance of the leads. Not that much anyway, but I'm being pedantic. Here we go. Let's stick this one on here. And hopefully it doesn't break off, and hopefully it grabs it. There we go. There's one there. There's one here. Come on, get on that tinned bit. Oh dear, I'm on the resistor leg that was in there. Sorry, nothing would have happened. Come on. Ah dear. It's going to be difficult. I don't know why, because yeah, that's just there. That's tinned, so it should connect there. That's tinned. It's so fine, it's hard to grab. Okay, I'm also at 1 kilohertz. I'll put it down to 120. It wants me to calibrate it again. But for some reason, I think this coil, the fine wire, is open circuit. So, oh dear. There's a start. Let's have a look. Got these little tape down bits, which they use for nulling. I'll just lift these off and I'll just make sure that the wire is actually going into the loop. There's no way known that I'll be using this coil again. Yeah, that's it. And it's actually tinned on the end. I can see that. So on there. And here's this one here. I'll just, yep, that's the other end. So why are we not getting, well, first of all, I'm going to put this on here at 120 and then we're going to have to calibrate it. Okay. Okay, so now we're calibrated. Don't be difficult. Oh, there we had movement. We had movement. Ah, the wire's so fine that it's having a hard time to bite it. What? That's connected. Oh, get on there. I saw it connect, so maybe these are not as tinned as I think they are. Let's have a look. I'd leave a big blob of solder on there because it's easy to connect to. Normally, if you make a coil, don't do things like that. It acts as a re-radiator. It acts as a target. It'd be like putting a little eyelet inside your coil and it would just be reactive. So anyway, let's get on this now and see if it sticks. Especially on the end bit here, hopefully. Yep, there we are. We have, oh, come on. It wants to measure. It's not that high in ohms. God. For some reason, it doesn't want to measure. Come on, you are connected. Okay, very strange. Well, we can get around that problem easy enough. I'll use this meter here. I'll just calibrate that down. So we take into account the leads. Not that it's much, it's only point something of an ohm, but that's close enough. 0.002. So we're not going to worry about that. I'm not going to worry about my fingers on this either, because I'm millions of ohms and this is nothing. So I can just stick it on that metal there, and there you go. 16.3 ohms on the receive winding. Now, if you know anything about resistive losses at frequency, that 16 ohms will multiply into a very large reactive resistance. Let's have a look on the transmit winding here, which I've already done, but I'll do it on this one because it's really accurate. Come on, I've got to get it. It's got resin on it. It's hard to get through. So the actual winding here, if you look at it, very low. I'm squeezing it hard as I can. It's about 0.28 of an ohm. That actually hurt and dug into my fingers. But anyway, so guys, this winding here is okay. Just remember, a non-circular coil winding is basically starts cancelling its own field. The closer these wires get to each other, the bundle, when you start squishing it together, you start getting field cancellation. It won't go as deep. Okay, most efficient coil is a round coil. I don't care what anyone says. Ellipticals are great for pinpointing, but you do lose depth when you squeeze the sides in to make an elliptical coil. It is pure laws of physics. It does that. I'm not going to go into great detail on it. Trust me on that you do get field cancellation when you start deforming a coil. That's why all the most efficient coils in the world are round. You do not see triangle ones. You do not see odd shaped things. You probably will from people's marketing perspectives. They may say things, but yes, I know why you have elliptical coils. I know, because I use them. But there is a trade-off. No free lunch. It's all good. Turn off, save the battery. That thing sucks batteries like crazy. So anyway, how do we make a better coil? How do we make a better DD coil? First of all, if you really want to know how to make it, I'll tell you how to make it really good. Okay. First of all, you can utilize a winding like this white transmit winding here. Okay, no problem. What I would do, I would make another one of these out of litz wire. The same. I would make it identical. It'll double the weight of the coil, near enough, because that wire there is not very heavy. And I would not use double D cable. I would get 2 mono cables, and I would somehow, very carefully or whatever, plastic weld them together. It's a big thick cable, and you'd have to modify the plug that goes into the detector as well. Now, the other thing you can do too, this, I haven't tried this. This might be worth experimenting with, but you've got to remember that on the transmit and the receive input lines on the detector, the transmit has its own damping resistor that's switched in and out. So it's not in during receive. Otherwise, it would probably, if it was connected in the circuit, it causes noise and also diminishes anything you're receiving. But in a double D, the trouble is what you need in the detector is 2 coil damping circuits. Okay. These are all my little trade secrets that I don't tell anybody about usually, but if you put in a double damping circuit, you can then damp with separate resistors on both channels. Up comes your receive levels. So you can use a big fat coil, another big fat coil, use an adapter that run the transmit and one receive line on one big coil, and run the receiver on the other coil. And you can do all sorts of wonderful things, and that will improve the efficiency of a double D design out of the universe. It will be quiet. It won't have hardly any losses. It'll be well behaved. and you can run it at higher frequencies without more losses compared to a, well, basically it'll work like a double mono. So look, just because I said that, that's going to happen now. Someone's going to build it. I guarantee you, it'll be commercially on the market within 6 months. And if it's not, I'll give up detecting forever. So it will come out, maybe not 6 months, maybe 12 months. But they're all clamoring for marketability, points of difference to make a better coil. Because Minelab's brought out these destined for Africa. Sorry, can't send it to Africa because all the governments changed the rules and regulations over in Somalia and Sudan, that people are basically stopped from detecting because of the government wants to do commercialization, don't they? And little self-functioning prospectors don't really provide much to the government, where a commercial entity will have to pay big fees to the government. So that's what's happening there. And that's why all these 45s that were destined for Africa are being pumped into the market. So they say it's a re-release. Do we call it a re-release? I suppose that's what they're saying. But yeah, it's just a, swings and roundabouts in the marketing of detectors. So that's my thing on double Ds, guys. I would not make a double D. No way would I make a double D like that. I mean, if it was just going to be quick, easy, something to, flog the detector with, basically, sell it. Australian terminology. Flogging means selling. In other parts of the world, it means flogging means whipping. So don't ask me why. I don't know. But yeah, I would make it less lossy, and I'd even change the internals of the detector to handle a better type of call. If you really want to, you can put a subboard in there, put a double, just come off the existing damping MOSFET, run another MOSFET device, and stick it on the receiver windings, and don't put one in the coil, right? So anyone pinches your coil is not going to work on their detector, but you'll probably have a different plug on it anyway, because with the dual fat mono cables, it'll be very hard to interface. So you possibly might have to make a junction box. You could make a junction box. What you do is you just join the braids together, have the inners go to the respective pins, which is probably pin 3 and pin 4, and you join pin 2, pin 3 together, and join the earths, pin 5 and pin 1, and transmits on pin 2. And you could probably I would do this. I'd have the cables go into something I 3D print as a little box. Around the cables, I would obviously put some sort of tape or heat shrink around the cables and around the braid connection. And if I could heat shrink the whole thing to a degree and leave a little bit of metalwork there, probably on the pin, you join the earths together, get a copper wire, and preferably tinned copper, 22 gauge, something like that, not critical. And off the ground pin, wind a coil on the outside of where all the braids and the connections are for that cables, so you're not going to get any capacitive reactance putting your hands into the coil plug or on the coil wires. If anything happens around that area, the detector does the woo 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 bizzo. So you could do that and make a really good stable setup. So then all you need to do is then convert that from your little adapter box into a plug. You could probably, you need to stabilize it because it's not very long. You don't know if you want the metal housing. You could put it on a short cable and have it very close, but I'd pull within reason, because you've got to do it up. It's hard. Think about it. You've got to think this through. That you'd have to be able to turn the nut onto the thread on the detector to hold it stable, and you'd have your little junction box. So what I would do, because I thought this out about 5 seconds ago, I would have a tapered junction box. So it would look like more like a pyramid type thing, but you know what I mean. Not just so the fat bits would be on the coil end and thinner towards the detector. That's how I would do it, and that would make a fantastic double D setup. My God, it would be good. You'd be able to run probably more gain. You'd be able to clock your detectors super fast, and you're going to get a lot less ground noise as well, just because of the geometry of the coil. The way, a lot of the coil directly under, the receive coil directly under the transmit coil is not being energized, and you don't get that noise. And also, it'd make a bloody awesome cancel coil for cancel mode. The reason being is that the coils are matched. Because these things are not matched, you put these in cancel mode in the room, turn the gain up, and it becomes noisy because it's not cancelling properly. It just doesn't. And also, the reason it doesn't too is because the damping resistor, we got one getting switched in and out on the transmit line, and the receive ones are constant. There's your imbalance there too for a resistive load. So, you've got a resistance across the coil in receive mode, and the other one's gone open circuit. So what do you expect? So, if we look at all this in great detail, we can see that our detectors are actually limited by the coil design. Now, using a mono will, greatly overcome all these problems. So, you don't need resistors in your coils and things. You can utilize the damping circuit inside the detector. And, like I say, with all this stuff, the enemy of having a good signal back to your detector, and also probably transmit as well, is the thickness of the cable, thickness of the conductors. You don't want resistive losses, and you also don't want high capacitance. So my methodology out there would be use a thicker transmit mono cable. Instead of being 6 mil outside diameter, make it 8. It's not going to add hardly anything weight-wise to any. It's a fraction. It's going to, maybe, I don't know, 20 or 30 grams or something maybe. I haven't done it, so I don't know. I'm just estimating. So you could do that, run a thicker mono cable, and if you keep everything the same and just spread the shielding out from that center, the capacitance drops off like crazy. You might get in at 20 picofarads over a meter and a bit of cable, 1.2 meters of cable. You might get, might be 20, 30. That means you can absolutely run the fastest transition times. So, you're not getting lag in your damping. You've got to get rid of that flyback energy quick. You can run quicker receive, turn on windows, everything speeds up. It makes for a better detector. So, it's the facts of life. Everything's made to a price and made to just do the job, if you want to ask my opinion. So, and if, even the way that's made, right, I would improve on that as well, but you don't have to. It's going to make probably 5 or possibly 10% difference. Yeah. I'm not talking about the receive. I'm talking about the transmit bundle. There are other ways of doing it. I would experiment. I would have a flexible geometry, and I would experiment. You don't have to have a coil with that, one overlapping the other like that as much. You could actually make it more of, rather than just running flat down there, you can actually make a triangular shape. Okay, not with sharp corners, but a rounded triangular shape. So this one would come more into the center. Can't do that holding the coffee, but I'd have it so that the transmit would come more into the center here and come back, and that would go there as well. And the other thing too, if you really want to know, that doesn't have to go here. It can go there if you want to make it smaller. It can run there. It can run there. It'll just run as a dual loop coil. You can then phase change it and do whatever you want. There's lots of things you can do with coils, and they're not done because people don't do it or they don't see a need to do it. Where as probably a commercial thing, but you can do it and you'll get benefits from it. You know, there's lots of ways of doing things. Like, I'm not going to go and give all the magic away, but there's ways of doing it. Make a do the same thing what I just said with the double D. Make a concentric, right, and put another damping circuit inside the detector. It'd go like a house on fire. It really would. You have a lot of energy in the ground and very efficient pickup. Even though with a concentric, depends which way you want to do it, you can actually have a phase changer in the detector if you're running both the same inductance coils. You've got to take into account too that the same inductance is going to have more turns, it's going to have more capacitance. So maybe you may need to compensate for that elsewhere. I won't go into that too much either, but it will have more interwinding capacitance. If you want to be really clever, you could run you can run two receive coils in there. You can run 3, you can run 4 and co-phase them together and get more capture area. There's a lot of things you can do, but then if you do stuff like that, it's not going to work very good as a cancel coil because it's going to introduce a lot of imbalances. But might be hard to pinpoint. You might have to go, there's tons of stuff you can do and no one's done it. It just amazes me. I've watched this for years and years and years. How come no one's done that? Why haven't they done this? It's, damn well, it's all to do with capture area and how big targets are. That's why people started making flat wound coils, because they tried to spread the field as far in as they can to make it sensitive to, like I've said many a time, makes it more sensitive to tiny targets closer to the inner part of the coil, of course. Also, probably as it goes under the windings, and then you trade off depth on bigger targets for that. So, it's funny if you have 10 coil designs, all different type of windings but the same size, and you have targets at various depths. Some coils will get them, some won't at all. Some will give a massively strong signal. Some will just be really weak. And then you do the inverse of those coils on different targets, and they'll pick up the bigger targets or smaller better again. So that's how it all works. It's horses for courses, and the goldfields your course and the detector coils your horse. Funny way of putting it, but basically, that's what horses for courses means. It means what's the track like, if it's soft or hard or whatever. That's tons of info I've given you there to make really good double D coils. If you want to do it, you can do that. But like people were telling me they want to use double D because they love this. This is contradictory. My coffee's gone cold. How contradictory is that? But they like using double Ds. Why? Right? Listen to this. This is a beauty, but I can understand the logic behind it. I love it. I love using double Ds because they're quiet. Why are they quiet? Do I have to actually say it? I just told you why they're quiet, right? They're quiet, but they're quiet to the point that you're not going to get gold. You're running double Ds against some of the newer detectors with super fast coils and clocked up to the max. Yeah, they're noisy. Of course they're noisy. They're untamed. What goes in the coil comes out and goes into your detector, basically. And what you're doing with these sluggy old double Ds on the faster detectors, however they're done, is you're just muffling everything. You just they can't do the transition in the right time, and it just desenses. That's what I found. I've got a double D coil over there I made myself. It's 2 mono coils out of phase on a double D. So it actually acts as a double D on mono mode. And it's as sensitive as hell. And it gets rid of all the noise. Even though I'm using crappy old double D coil cable, right, which is unbalanced in itself, it's a massive improvement than using something like that even in cancel mode. But yeah, with the high speed modifications that we're doing to the detectors to speed up the pulses and bring in the receive window and everything else, the double D coils, when I did my own tests, very, very deaf compared to a mono on anything whatsoever. And the other thing too is that when you flick the double D into cancel mode, for some reason, its performance increases. I haven't actually studied it too much. It only happened the other day when I was flicking between both, and I went, what's going on here? That's that coil connector that went into the mud and filled up with mud. So it possibly could be something to do with that, but I did clean it out pretty well. And it was a bit of mud went through and into the windings on the back of the plug. It may have been tracking out a bit or something, but I need to get it out there, preferably when it's not muddy, and try again and just do another test. But overall, my suggestion is, if the coil is not made correctly for the newer type detectors, I would avoid using older double Ds. I will use it here, the old double D, because it's a worst case scenario. If I can't make it work on that, it's not going to work on anything. Well, it'll work on newer coils, of course, but if I can't make it work on that, it's people hook older coils up and things made out of tin plated wire and all sorts of old stuff, and it won't work at all. So it's a yardstick. A GP coil, the older one I use, is a yardstick as such. So just things I've said, especially about dielectrics, this stuff here, that's actually that's insulation foam. I think they use that in trucks for insulation, and they just put it through a horizontal bandsaw and cut it to the right thickness. So if you want to know how to do that, yeah, these are all routed out. The grooves are routed out with a router, plunge router of some sort, and they're not hard to make. But the thing is, rather than use this, use surfboard foam if you can get it. It's open cell structure. It looks like something like a violet crumble or something like that. But it's got lots of air. Air is your friend with coils because air doesn't saturate. It doesn't have dielectric losses, and it doesn't have a dissipation factor that actually chews up your high frequency, high speed signals. So if you can get as much air into your coil design as possible, don't fill it up with resin. Look, I know that coil there is full of resin. I can feel it, because if you got to stabilize your coil, okay? You got to stabilize it, because if the windings move at all slightly, it'll do the woo woo, right? It just will. It'll just move when you swing it even, and if you bang it on the ground, it's going to make worse a noise. But what you want is a low dielectric glue. And the only way to test that is you need to get glue, and you need to set it, and basically put it between two metal plates, make them all the same, and measure the capacitance. You can't measure, well, you probably can measure the Q factor if you want to get really technical, measure the dielectric losses at frequency. But, the capacitance tells a story. Usually, the lower the capacitance, the lower the losses, because there's less material giving that capacitance in the first place. So, glues are important. Don't use water-based glues. Don't use epoxy resins. No good. Very high dielectric, 6s and 7s for memory. If you can get a glue made out of Teflon, it'll be a dielectric of 2.2. Next best thing to get glues out of, if you want to make a way of mounting it, melt polypropylene and use that as a hot glue. That has a very low dielectric constant, followed by polyethylene. Has a little bit higher, but not as good as air, of course. And if you want to be really, really clever, I'll tell you the biggest secret of all. If you use cotton, people don't know this, but I'm going to tell you because it's really good. Cotton has a dielectric constant close to 1. It's the same as air, okay? So wind your coils in cotton. But the caveat is don't ever get moisture in there, because then it'll have a dielectric of a house brick, right? In other words, it'll just won't work. So if you can get cotton to hold your windings, and also there's other things about the windings too. You really want to have a spacing between each wind. You don't want them hard because then you get domain cancellation. You want to separate your windings by 1/3 of the strand diameter. Okay, I've measured this and I know damn well it's accurate to get the most efficiency. So 1/3 strand diameter should be the isolation between the next strand and all the other strands around it, right? So that's what you want to do. Varnish, they use all that polyamide stuff. It's not the best dielectric as well. If you could actually get the strands of litz wire, and yeah, they use polyamide. You can use silk. Silk's got a horrible dielectric constant as well. But instead of using that material, if you could get the litz strands done in cotton, real cotton, and work it all out, get the strands right. Go look at New England Wire and Cable. Look at their litz wire charts for frequency, and you'll be able to look at, you get litz wire specifically designed for around about 30 to 40 kilohertz, okay? That is optimum. And then you want to look at the overall current you're trying to get from the transmitter, the voltage, current. You can work it out easy enough. You're just going to plug in the inductance, the capacitance, all capacitance, and time constant of the pulse, and it'll give you, it'll work it out. We'll just tap the camera. So there are a lot of criteria. You can go and measure all this stuff and do it scientifically, make a really good call, but I'm just telling you the easy way to do it. So if you actually wrapped each strand in very fine cotton, put the strands all together and wrap the whole lot in cotton, the most efficient coil you could ever make. Next to no losses. All you got then is copper losses, and you probably got a little bit of domain cancellation. But and use the best copper you can get. Be careful of copper. Sometimes copper wire is not copper wire, and some of it has additives like other materials put in the copper, and it has not the same conduction as what pure copper has. Be careful. Always get a sample and look on a wire chart what you should get over, say, a meter. Greater is better because you'll get more accuracy. But it's very hard to measure. Or you could, I suppose, you get a spool, measure it, and then put it on a spool. You got to do it on DC. Don't do it with anything with a frequency component because it'll go crazy. It'll say it's hundreds of ohms. It won't be. But you got to be very careful how you measure things. You got to know what you're doing. But and also, yeah, don't trust copper. All the litz wire I got that. My litz wire, I got that 2000. I don't know, 2008 or 9 or something. I bought a stack of it and I got it made properly, and that's why I have tons of litz wire. I don't know. I think I could probably wrap the earth with it. I have it strand on strand, but there's tons of it, and yeah, it's specifically designed for very high frequency, metal detector used for the transmit coils, but you can also use it for receive. It works really well. What else? Yeah, basically, I've got to be in my bonnet about the double D coils, and it's just people persist in wanting to use them. And how do we make it better for people that want to use them? That's what it is. It's probably I don't know, bit hard. Maybe trying to convert a Muslim to be a Catholic or a Catholic to be a Muslim. I think you'd be pushing it really, really hard trying to do that. And people have their heart set using a DD coil over a mono. Well, that's what they'll do until they're shown the way, and then they'll probably do it a bit differently. But yeah, it is what it is, isn't it? Anyway, it's probably enough waffle on that subject. I think I've probably given everyone the crown jewels of making a good DD. Every aspect, just look at every aspect of how it's made. And yeah, I guarantee you someone out there is going to put dual damping inside the detector. You just take it off the gate wire of the existing MOSFET. Just split it between two 10 ohm resistors so you don't get any capacitive effects that can cause a problem, cause ringing. So yeah, probably 10 ohm resistors, small surface mount, make a little subboard, put on an IRF 214 or something of that nature, or whatever they use there. What is it? VNZ, VNZ 2120, I think it is. Anyway, it's Zetix, who call themselves diodes now. It's a ZVN 210, might be a 2106. I can't remember off the top of my head what it is. I just use them. I don't read. Hang on a sec. ZVN 2106G. So you got to remember the G, right? Otherwise, you'll get one with 3 legs, which is the E-type, inline, like old style. The G means it's going to be like a TO223 package. So you probably have to heat sink it a bit, but you can do that, and then make your own double Ds and don't have internal drag damping inside the coil, and just run it in the detector. You could probably make a separate damping circuit and put a switch on the detector, switch it in, switch it out, really close to the coil connector. Because if it's just floating there doing nothing, it's not going to do anything to the detector. So you could do that, and that allows you, so when you run a mono, you're not double damping. That would be a problem, wouldn't it? Because it connects on the both channels on a mono. So you probably want a switch. You hate switches when you're switching stuff like that, but silver contact switch, something high quality. Don't use a crappy switch. Use a good switch. Make sure it's like a C&K switch, like the toggle switches they already use. Use one of those. They're okay. And yeah, the switch has to be rated for probably 200 volt breakdown, because if you're going to do things with mono coils and that damping resistor circuit still there, it will probably may think about wanting to arc out. So you want a high voltage switch. But yeah, it's given everyone a lot of food for thought there. And if you want to do it, do it. It's look, I've said all this. I guarantee you that it's going to come out. It'll come out commercially. Someone will do it, right? You could even, could you do it? Let me think. Yeah, you could even, let me think about it. You could use, in the secondary damping circuit, might unbalance it a little bit, but you could utilize a dual MOSFET setup in there, and leave it connected all the time. Yeah, you could just use a dual series MOSFET connection with the damping resistor, and yeah, and then all you need to do is reprogram the microprocessor and the detector on the back menu, have mono or DD, and put a control line to it and switch it in and out. um, there's ways to do it. Actually, put a little tiny receiver in there with a phone app and turn it on and off with your bloody mobile phone. It's not that hard. It can be done, but I wouldn't go to that elaborate way of doing it. I try and do it simply. I'm just trying to think of a simple way to do it. I know how I'd have to think it out, but you could actually you could make an auto sensing circuit and put it into the detector that turns a MOSFET on or off. Just have series MOSFETs, two of them, because low ohm things, and have one that. Let me think about it. I'm thinking about it on the fly, but you could do it. You could actually have a auto sense circuit, because when you put on a double D, right, it joins all the 3 pins 2, 3, and 4 together. Okay, so you could sense that on a double D, they're not all joined together, and they are with a mono. You'd have to be careful that if you do that your little circuit doesn't introduce noise. You probably have it that you turn the detector on, it senses, and then turns off. Right, isolates itself somehow. And you could do it too. If you want to be really clever, you could probably have a sensing circuit there. You could probably make it floating. You could just utilize power from the existing switch mode power supply and have like little isolation transformers and rectify it on a subboard and have it a floating system, so there's no reaction to ground. But maybe be careful too, because you'd have a bit of capacitance, whatever you're using to drive it. If you're using a transformer, can you do it? Makes me think this stuff. I'll come up with a way to do it. You watch, or someone else will. Maybe someone else should do it. I don't want to do everything. So, guys, that is the biggest rundown I could tell you about double D coils. I don't think there's anything else. There's only other coil configurations, but I don't want to go into that because I've got to have something up my sleeve, don't I? But that's the thing with double D coils. On the newer detectors, they are woeful unless they're specifically designed to run at the frequencies the new detectors run at. So, yeah, again, got to use the right coil for the right machine. It all has to be set up properly, and just be careful of copper. The additives in copper nowadays, never used to be, is now. And also just the way cables are made and stuff like that. Yeah, leave it there. And yeah, if you can do something with that, great. If you can't, well, okay, very good. I'm just seeing payments go through. All good catches, guys.